And PhD training is in the realm of chemical physics, and today I'm going to run through a few undergraduate level physics questions. So our first one here reads: a proton, which has a charge of plus E and a mass of MP. A deuteron, which has the same charge but double the mass, and an alpha particle, which has double the charge and 4 times the mass of a proton, are accelerated from rest through a common potential difference. Each of the particles enters a uniform magnetic field with its velocity in a direction perpendicular to the B field. The proton moves in a circular path of radius rp. In terms of rp, we need to determine the radius of the circular orbit for the deuteron and the radius for the alpha particle. Sorry, 1 second. Sorry about that. All right, so to start us off, we're just going to deal with the proton. So if we're looking for, so if we're talking about a proton traveling through a potential difference, delta U is equal to Q delta V. Minus Q delta V. The reason I say minus Q delta V is because all particles move from high to low potential difference, and so, or from high potential energy to low potential energy, so delta U will always be negative. And so delta KE, or the change in kinetic energy, is always going to be negative the change in potential. So it will just equal Q delta V. Now if the particle starts from rest, that means that it's KE final minus KE initial is equal to Q delta V. And that means, since it starts from rest, that's 0. So our final kinetic energy is just equal to Q delta V. And this will be true for all of our particles. The only difference is going to be what the charge is, but the potential difference is the same. So that means 1/2 mv squared is equal to Q delta V. And then we can solve I've got some extra stuff here. We can solve for our velocity by just rearranging this expression. So our velocity is then 2Q delta V over m all square rooted. And for our proton, this V, this V is going to be equal to 2E delta V over MP. Okay, so there's our velocity for our proton. Now, if we so this is our velocity leaving our charge, our delta V region, prior to entering our B region. So the force on a charged particle due to a perpendicular B field is QV cross, or QV, I'll just put it in properly, I guess, QV cross B, which just means that, at least in this case, that if V is perpendicular to B, which it is, that the expression simplifies to just QVB. Okay, and so then the the way we rationalize now, if it moves in a circular path of radius RP, so this force then has to equal our centripetal force. Okay, so our centripetal force is F equals mv squared over r. So then this, our magnetic force, is our centripetal force, so that means that QVB is equal to mv squared over r. Or rearranging for our r, because we want our our radius for our orbit. So that means for the proton, we have, rearranging this, R equals mv squared over qvb, although I guess at this point this is still just general, so mv over qb. So that's our radius expression for any of the particles, actually, but specifically for the proton, we will have Rp equals Mp over Eb. And then recall, before I had that V equals root 2e delta V over B, or MP, sorry, over MP. So substituting that in, okay, and then solving this through, so MP over root MP just leaves you with the square root MP, E over E. A square root of E over E is just going to give you a square root of E on the bottom. So this is going to give you a 1 over B, square root 2MP delta V over E. Yeah. So then that is our RP. So that's our radius for our proton orbit. And obviously that'll come back, but first we need to solve for the Deuteron and the alpha particle. So for the deuteron, we have our charge is plus E, and our mass is 2 MP. And so we can take some of the expressions from above. So recall that from our kinetic energy expression, we have that Ke final is Q delta V, or 1/2 mv squared is Q delta V. So then V is 2Q delta V over M square root. Okay. So then we can just plug in our charges and our mass. So the V for our deuteron is just the square root of 2E delta V over 2MP E delta V over MP. Okay. So there's the velocity for our deuteron. And then again from our circular orbit, we have that R equals mv over qb. So that'll be the radius of all of our orbits. And so plugging in the values, we have 2mp vd over eb. And then plugging in this value for the velocity, and then again, we can move the E inside the square root and the MP inside the square root. And now to compare this to our P, right? Remember that our P is 1 over B square root of 2E delta V over MP. So we almost have that, but this 2 needs to be moved, a bit of it needs to be moved inside the square root. So recall that 2 is root 2 times root 2, so one of those root 2's can go inside. So then our D is root 2 over B, root 2 MP delta V over E, which is just root 2 RP, right? So I've just used this expression and substituted in for all the rest there. So it's just square root of 2 times the proton radius. And that's all we were looking for the deuteron. And then for the alpha particle, we want to repeat that. So for the alpha particle, we have a charge of 2e and a mass of 4 mp. Again, returning to our kinetic energy expression, we have that V equals square root of 2m 2e delta 2q delta V over m, I believe. and write that one down. And I want to derive it every time. 2q delta v over m, yeah. So, substituting in our given values, we have square root 4e delta v over 4mp. So those cancel. So that is just equal to the square root of e delta v over mp. Okay, so then that's our alpha particle mass, or alpha particle velocity. And then our radial expression is just mv over qb. So our alpha particle radius will be substituting in the relevant values for mp v alpha over 2eb, and then substituting in our velocity for our alpha particle and dividing out this 2 here, 2mp over eb square root e delta v over mp. And then recalling that our and then moving in the MPs and the E's, we have R alpha equals 2 over B square root MP delta V over E. And then remember that our P is 1 over B square root 2MP delta V over E. And then we can move the part of this 2 inside by using that 2 is root 2. So then our alpha is just root 2 over B square root of 2MP delta V over E, which is just root 2 RP. And so then that's the radius for the alpha particle. And so then we have that, just to wrap things up here, we have our P for the proton, and then our alpha, or our deuteron, is root 2 RP, and our alpha is also root 2 RP. Okay, so now if we check the solution here, so that's the B field force has to be equal to our centripetal force. So then we can solve for R, which is the expression we got for our P, a little bit differently arranged. But then using that, we get for the deuteron root 2 RP, and for the alpha particle root 2 RP, which looks good. So the solution is correct. And I'm just gonna quickly do that. Okay. How does the electric potential energy change as the electron moves? So I'd say this is kind of open, but our electron potential energy is U equals 1 over 4 pi epsilon naught Q1 Q2 over R 1, 2. So that's the separation between the two charges, Q1 and Q2. If we take Q2 2 here as our electron, then we could say that this is 1 over 4 pi epsilon naught Q1e of, I should say, minus over R12, because an electron's charge is actually minus e. So then if we plot this, where this is R and this is energy. Turns out that I'm writing sideways on this. And that's energy, where this is positive energy and that's negative energy. If our charge is positive, then we've got a 1 over R relationship that is negative. And if Q is negative, then we have a 1 over R that's positive, pretending that these two are symmetric, because they should be, as long as the charges are equivalent anyway. And so if Q1 is less than 0, so it's negative, then we have a repulsive force that goes off to infinity as R approaches 0, because it takes more and more energy to force two equally charged particles closer and closer together. But then it goes off to 0 as R goes to infinity. On the other side, if Q is greater than 0, so we have a positive particle, then this goes to negative infinity as R goes to 0, as they want to be as close together as possible. But then the energy still goes to 0 as R goes to infinity. So these two will eventually meet each other as R goes to infinity. Now if we, so that's one way of looking at it. If we look at the solution here, then the solution is more in the direction of electric field, which is fine. One thing I always find handy for for actually everything, is that the force and the electric field are related. No, I should do this. The electric field can become the force with a multiplication by charge. The potential energy goes to force with the multiplication with, I guess, the multiplication of a derivative. Or you can go the other way with an integration. The potential, again, is multiplication by charge, and the potential becomes the electric field with a derivative. So that kind of connects each of these quantities. And so what's in the solution here is then your potential, or I should say this way, is a dx. So your potential is your electric field dx, or dr, I guess. It depends on what distance unit you're using, but if we're just going to consider it in one dimension for simplicity here, so your potential is just e dx integral. And then your potential energy is then multiplication by charge, so that it would be QE delta x. Again, just for simplicity, turning the integral into a delta x, so a change in your distance. And so, oops, I shouldn't have written it like that, but your potential energy this would lead to your potential energy being QE delta x by going this way around this little box, which is also true, but just expressed from the electric field. So if you know the electric field, then you can get the potential energy that way. And all this says is that your potential energy is just whatever your charge is, whatever the electric field you moved the charge through, times delta x. And I guess that would be actually a change in potential energy. So it would be, this would also be a change in potential energy, because you'd have to give it some zero, but you can always assign whatever zero you would like for potential. And yeah, potential energy, and a charge does have potential energy by virtue of its position, which this kind of expresses, but then I think is more simplistically shown through just Coulomb's law. But also if you have not point charges but some electric field, then you could express it like this, and there's many other ways to do it as well. So I would say the solution is correct. The change in potential. Okay, so for this one, this is a momentum question. A football player, and a football player of mass equals 95 kilograms, is running at a speed of 5 meters per second, 5.0. A second player of mass 140 kilograms is running at a speed of 2.5 meters per second. And it doesn't say direction, but I'm assuming, with my rudimentary understanding of football, that they'd probably be coming from opposite directions, and they'd likely be running towards each other. So I'm giving the velocity for this guy a negative 2.5 as they're moving toward, as he's moving in an opposite direction to the first guy. A second player tackles the first player, so they move together after the collision. Now these guys apparently have even less of an understanding of football than I do, because neither of them are even holding the ball. I don't think you can tackle each other that way. Maybe. And they hold each other and move as one with some final velocity. Now, the mass in this case, I should have put little ones here. 1 or 2. So now our mass is going to be m1 plus m2, as it's the total mass. So neglecting my terrible drawings, we're going to move forward, and I'm also going to move this over here and say, so the idea here is that your momentum initially must equal your momentum in the final case. Your initial momentum is m1v1 plus m2v2, which is 95 kilograms times 5 meters per second plus 140 kilograms. 140 kilograms times minus 2.5 meters per second, which, if we run this through our calculator, comes out to be 125 kilograms meters per second. All right. And then our final momentum is going to be m1 plus m2 vf, where vf is the velocity, or the speed in this case, that we are solving for. I guess velocity we are solving for. And so that's just going to be 95 kilograms plus 140 kilograms times VF, which is equal to 235 kilograms VF. And then now we're in a place to solve this, as these two quantities are equal, right? Our PI equals our PF. So then we can just say that 235 kilograms VF is equal to 125 kilograms meters per second. VF is then equal to 125 kilograms meters per second over 235 kilograms. The kilograms will cancel, leaving meters per second. And this is equal to 0.532 meters per second. And this is in the positive direction. So my original drawing was correct. They continue to move in the positive x direction. Now if we look at the solution, so directions weren't inherently given in the problem, and the figure that's given here isn't shown. So the person who did the solution here took the second velocity as positive, which definitely will change the answer. It means it's still technically correct. I don't think it makes as much sense because the second person is traveling with a smaller speed, so it's kind of tricky for that person to catch up to the person traveling a higher speed. But if you use a positive velocity for the second player, then the momentum would come out to be 3.5. And again, it wasn't given in the problem. I'm assuming the way I did it is likely correct, but all the math in this is correct, assuming player 2's speed is positive. But I would say the math here is all correct. The only problem is the sign on the second velocity. Okay. Okay, so this one is how do the speeds at 3 different times compare with each other? So I'm just going to sketch out the plot that you can't really see very well. So we've got X, and we've got Y, and the plot has a parabolic motion like that. And we have tangential velocities here, here, and here. This tangential velocity is not very tangential for me. So I'm just going to make it a little bit more tangential. There we go. So V0, V1, and V2, T2, T1, and T0. This one should be slightly more flat than it is, but we can just pretend. Okay, so it's asking how do the speeds at 0, 1, and 2 compare with each other. Remember that a velocity, say V0, is going to be some x component plus some y component, while our speed is going to be the magnitude of this, which is the square root of Vx squared plus Vy squared. Now this problem doesn't ask us to do any actual math, but I'm just pointing that out for now. So then at T1, which is the peak of our orbit, Vy has gone completely to 0, but gravity only acts in the y direction, so that means that V1, our velocity, is still going to be Vx x hat. So it'll be an identical x velocity, assuming no wind resistance, of course. So our speed is then just Vx. So it's completely just the x part. And obviously, as this is x plus y, and this is just x, this is going to be less than our speed at 0. So at 1, the speed is less than our speed at 0 and is, without wind resistance, exactly equal to the x component velocity that we started with. And then at T2, acceleration has now brought our Vy all the way to minus Vy. So we've gone from 0 at the apex to minus Vy at the landing point. Okay, so it's all perfectly symmetric. So then at T2, Vy goes to minus Vy. So our V2, our velocity is just Vx x hat minus Vy y hat. But then if we look at our speed, it's just the square root of Vx squared plus Vy squared, because a minus sign when squared becomes positive. So then that exactly equals our 0 speed. And so to wrap it back through, right, if we have some speed at t0, then at t1 the speed is going to be less and exactly equal to the x component. And then at t2 it's going to be exactly equal but acting in a negative y direction. But x is maintained throughout the whole motion. So if we look through the solution here, that basically talks through everything and says the velocities v0 and v2 will be equal in magnitude and will be greater than the v1, which is what we said. So that looks good. Okay, and again, I'm just going to sketch this out as it's cut off a bit there. So what we're given in the problem are 4 cases for a mass on a spring. And my spring is going to be a rather janky spring, but that's okay. And these might not be overly straight, but again, we can deal with that. Okay, so then this is minus a root 2 over 2, 0, a over 2, and a. Okay, so assuming that our mass on a spring, and they give us that the spring has a spring constant of k. Assuming that our mass on a spring is pulled out to A and released so that it goes back and forth between A and minus A, and there's no frictional forces that prevent it, that slow it down or anything like that, then it wants to know the kinetic energy at B. So when it's stretched to A over 2. So the potential energy for a mass on a spring is just 1/2 k x minus x naught squared, where that's our equilibrium distance. Now in this case, we're using 0 as our equilibrium distance, so that makes things nice for us. So we can just say it's 1/2 kx squared. So then from that, and because we want to know the kinetic energy after we've released the spring at A and when it reaches A over 2, or we could do it at any point really, but I'm choosing A for a reason. It's because the potential energy at A is 1/2 ka squared, and the kinetic energy at A, which is the peak of the vibration, is 0. Right, so it always goes up. It goes from A to minus A, and the potential energy reaches a maximum at A, but the kinetic energy reaches its minimum, which is 0. So then the potential energy at B is 1/2 k times A over 2 squared. And we want to know what kinetic energy at B is. So our change in our kinetic energy is always equal to the negative change in our potential energy from conservation of momentum or conservation of energy. So if we want to know what the KE for B is, then it's just equal to the potential energy at B minus the potential energy at A. Minus that. There we go. And so we have those expressions there. So it's just equal to minus 1/2 Ka squared over 4 minus 1/2 Ka squared. We can bring the 1/2 k's out, and the a squareds over 4 we're going to have to bring together by just using common denominators. So minus 1/2 k, and then this is going to be a squared over 4 minus 4a squared over 4, which is just minus 3/4, so the minuses will cancel. And we're going to get 3a squared over 8 with a k in there somewhere. There. So it's going to be 3k a squared over 8. So the kinetic energy at B is just 3ka squared over 8. If we look at the solution, so it uses the velocity of a mass at a simple harmonic motion. I'm pretty sure the velocity you could just back out from this, but okay. They should be the same, so presumably they get the same answer. So putting that in for the speeds, they get a speed. They use the kinetic energy expression for velocity to get this kinetic energy, but it's in terms of omega. But omega is root k over m. And so then they get that the kinetic energy is 3k a squared over 8, which is exactly what we found. But I'd say a little trickier. I think it's kind of in the backwards direction, but the solution is correct. And so similar question, so I probably should have actually left that up, but that's fine. So this is the same sketch. So we have a mass or several masses on springs. Or I guess several instances of time of the same mass on a spring, all with the same mass, and that's A, that's A over 2, that's 0, and that's minus A root 2 over 2. Okay, so the potential energy for a mass on a spring is 1/2 k x minus x naught squared. In this problem, our x naught is given as 0, so it's going to be 1/2 k x squared. And it asks which of A, B, C, or D have the highest potential energy for the system. And so as it's a quadratic relationship in our x, we just want the highest value. So for A, the potential energy will be 1/2 Ka squared. For B, potential energy will be 1/2 Ka over 2 squared. For C, our potential energy will just be 0 because x is 0. And for D, our potential energy will be 1/2 K root 2 over 2A squared. It's negative, but a negative squared is positive. So we just want the highest value, so it's got to be just A. And so the point of highest potential energy is always the maximum displacement from your equilibrium position. So in this case it's A because it's the highest displacement. The work is okay, so it kind of just describes spring motion, and then it says position A and D represent the maximum, but I would say this is an error. Position A is the maximum, position D is not. I'm just going to say no. Okay. A string is wrapped around a uniform solid cylinder of radius r. So we have a string connected to a mass. The cylinder can rotate freely about its axis. The loose end of the string is attached to a block. The block and cylinder both have mass m. What is the angular acceleration of the cylinder as the block descends? So the block is going to have a force due to gravity, which is just mg. And that force is going to act through the string at the point where on the cylinder. So the force on the cylinder is just mg, and it's acting radially. And so if we want angular acceleration, then what we're looking for is our torque. So just as in linear motion we have F equals ma, in circular motion we have our torque is I alpha, which is a nice parallel. So our torque is R cross F. So the radius at which it acts, cross product with the force, as they're acting acting perpendicularly to each other or at perfect right angles, then we can say that our torque is just Rf, which is just Rmg. For a circular disc or a cylinder rotating about an axis which goes through its center, the moment of inertia will be 1/2 mr squared. And so now we have everything we need to solve for our alpha, because from this expression we have that alpha is our torque over our moment of inertia, and so our alpha is Rmg over 1/2 mr squared, canceling m's, canceling r, and moving this 2 up top, we have that alpha is 2g over r. Okay, so looking through for the solution here, the moment of inertia is 1/2 mr squared. The weight of the block is the force which acts perpendicularly, so torque is just Fr, which is just mgr, which is what we had. the angular acceleration of an object, yeah. So as we said, torque is I alpha, so we can rearrange. It just comes out to be 2g over r. So the solution is correct. Okay. All right. I have time for one more quick one. So, I suppose this is my 8th, but I haven't been numbering them. So the moon's mass is 7.4 times 10 to the 22 kilograms, and it orbits at a radius of 3.8 times 10 to the 8 meters from Earth, with a period of 27.3 days. What is the angular momentum of the moon around the Earth? So, angular momentum is I omega, where omega is your angular frequency and I is your moment of inertia. Your moment of inertia is mr squared, which in this case is going to be 7.4 times 10 to the 22 kilograms times 3.8 times 10 to the 8 meters, all squared, which comes out to be 1.06856 times 10 to the 40 kilograms meters squared. Now, for our omega, that's our angular frequency, so it's going to be 2 pi radians over the period, but it's given in days. And so we need unit conversions, so 1 day is 24 hours, 1 hour is 60 minutes, and 1 minute is 60 seconds. So multiplying this all through, it is 2.66381 times 10 to the minus 6 radians per second. So now we have the quantities we need to calculate our angular momentum. So then L is just 1.06856 times 10 to the 40 kilograms meters squared times 2.66381 times 10 to the minus 6 per seconds, which is 2.84644 times 10 to the 34 kilograms meters squared per second, or for significant digits, 2.8 times 10 to the 34. Okay. So looking at the solution given, so it expanded the mode of inertia instead of using it directly, but that's fine. 2.84, that seems like there's a very last digit difference, but that's fine. So I'd say the solution is correct. All right, and then I'm going to stop this and say that's all the questions that I'm going to run through today. This has been Jeff Krause for OneClass. If you enjoyed this, please subscribe, and you can submit questions through the links below. Thank you.